Okay, this is chapter 6. In this chapter, we are going to look at the analog to digital converter module of the PIC microcontroller. And we look at some examples as well and how to actually use how to program the A to D converter. So analog to digital converter. So the current, the microcontroller that we are using, it has got, it can convert an analog signal into 10-bit binary representation. So it needs 2 locations to store, 8-bit plus another 2 bits. And the conversion results are normally stored in 2 registers. One is the low byte is stored in address L, and the high byte is stored in address H. And there are 14 analog input pins available. You need to program them so that you can have 14 analog to digital converter connections can have. They may be operating one at a time, or you can select them. So you can see a simple ADC block diagram I've drawn here, and you've got that's A and 0. That's actually port A. PA node need to be programmed, so it's called it's an A to D converter to that point and up to AN13, and there are various pins. They're not all up port A, and I'll show you in the next slide. And then we have got a register. By selecting the appropriate bits on the register, you can select the appropriate input to the A to D converter. So if you select this one, for example, that one, if you select that bit, anything you're connecting analog signal will go through the A to D converter for conversion. And so there are 14 separate analog inputs. The ADC voltage, there are reference voltages. One is the supply voltage VDD, and the other one is the ground voltage, other one is reference. So you can see in this case there are 2 positions where they are connected, and we have a positive reference voltage. You can provide that through that line, and then if you put this bit to 1, that will be connected. So that's your positive reference voltage go to A to D converter. If you want to have the negative voltage, also you can connect them through this and through that, and this has to be 1, then it will be connected that way. If it is 0, this will be connected to ground. So you can choose. So if you want to measure voltage differences, not just analog voltage into digital, but you've got 2 lines coming in, you want to measure the voltage difference, you will use this particular arrangement. And we have examples to show you. So the A to D can generate interrupt, so you can do many ways. You can actually program it. One is it can generate interrupt, and then you can go, when there's an interrupt, go to the interrupt service routine and read the data from those registers, or you can poll it until the conversion is complete. So once you enable the A to D converter, that means enabling means you put the switch. These are software selectable switches. When you selected them, you need to give roughly 20 microsecond delay for the system to settle and set up before actually you start to do the conversion. So we're going to look at this A to D module. This is the simplest module where once it's finished the conversion, 10 bits will be available, and this particular line will go low. That means saying the conversion is complete. To start the A to D converter, you first enable, you connect this line, and then you set this bit to 1. When it's finished conversion, this go done bit will go low, and that means it's converted. And then you have 2 ways of reading the data, which I come to the next line. In the next page I show it to you, and the lower 8 bits will be here, and then the remaining 2 bits will be here, providing the 10 bits. That is called right justification. If you go for left justification, you will have the first 8 bits there and the next 2 bits there. So you can have both ways. So anyway, in this slide, all we are saying that we can program the ADD converter the way we want it. There are 14 channels available. We can pick and choose the channel you want, and also you can decide what sort of voltage swing you want. You can decide whether you want to measure just a single voltage or differences between voltages. Now we just look at the address H and address L. So ADC output can be stored in two formats. One is called left justified, right justified. So if you set this ADFM bit, which I will explain in a minute, there's a particular register there, and in that register the 7th bit is ADFM bit, and if you set that bit to 1, then the result, these two results are right justified. That means the lower 8 bits will be there, the next 2 bits will be there. If you set this bit to 0, if you set this to is left justified, that means these are the most 8 bits and these are the next 2 bits. So that's called left justified. You can decide, depends on how you want it, you can go right or left. Most of the cases we go for right justified, and if you want to multiply this data by 2, you can just shift them by 1 bit in that direction, and then it will multiply by 2. So that's because you will find that there are empty space here, so multiplication becomes easier. And if you want to divide them, then you shift that way. And so you know that after you take the data, you want to multiply or divide. So you decide that in advance, and then you program it that way. And these bits are automatically set to 0. They are not used, but they are set 0. So you don't need to do an AND function to make it 0. They will be 0. When you do right justification, these bits plus these will be 0. Now there are 2 more bits on that particular register there. You need to use this register to program. After you have selected whether just right or left justified, then you need to have 2 more bits to decide what sort of voltage you want to give. So you can see that I've drawn here in this diagram. If you reference positive voltage, if you want that to be connected to the external world, that's here, you set that's equal to 1. That means that pin will be connected and it set up a reference voltage for ADD converter. If you decided that no, that's what you don't want, you want to set that to a supply voltage, this can be set to supply. So if you set this bit to 0, this pin is there, that's your supply voltage. So this line becomes ineffective. You are not using that line at all. And similarly in AN2, in this one, if you not want to use this line at all, then you set this VG1 to 0, so that connected there. So I will show you this with 2 examples, how we connect them. So basically, if you do this connection, if this condition, if you take that, that means your supply voltage is your maximum voltage and your ground is the lower voltage, and you can use any of these pins as an analog voltage coming in, and you select that one, and this voltage range has to be between 0 and 5 because this is 0 and 5. If you want a different range, then you have to give external voltage. And this is fed to this one, and when you enable them, A to D converter converts them. So it's important that you need to know what application you're going to use, what sort of voltage you're going to convert them, whether the voltage difference you're going to convert or a single voltage, then you select the bits appropriately. I've got 2 examples later on to show how do you select this one. So these 3 bits are important. I've explained that here. I've already explained it verbally, and it's there now. You can have a look. Let's move on to the next slide. Now we are going to select the channel. Remember I mentioned that there are 14 channels there, 14 inputs there, and you need to select the channel. Which channel do we select? So these 3 bits contribute to the channel selection. So you can see a table here. If you put all of them zeros, first channel is selected, which is called PA node, port A node, which become as an analog input now. You need to program it as well, but we'll come back to that. If you select, say, if you put the values here, say 10011, so if you put 1011, so 1011 is that channel, which is 11 channel, which is RB4. That's port B, fourth pin will become the port B4 pin will now become the input to the ATD converter. So you can choose out of the 14 the channels that you want by programming these bits. There are 4 bits there, so that fits in the 14 bit. If you put in all of them once, then the reference voltage will become 0.6 volts. That's another option available to you. On the other hand, you've got 2 more bits here, which controls the clock. At what is the clock frequency of the ATD converter? At what rate you want it to convert the analog signal into digital signal? So if you set both of them zeros, this is 0, this is 0, then the oscillator frequency, which is 4 megahertz, I think in our system, divide by 2, that is 2 megahertz. It will operate at 2 megahertz. If you put 10, oscillator frequency divided by 32, so it's a lower rate it runs. You know. And if you put 11, then the oscillator frequency is internally set up as 500 kilohertz. So they are the options available for the ATD converter. Again, we need to program this register, and we will come back to this one. When you want to start the ATD converter, you have to enable it. So this bit needs to be set to 1. And then when you want to start to convert them, this is enabling. To convert them, you need to set this to 1. And when you finish conversion, this will automatically go to 0. Then you know it has finished conversion. And we will use all of them. That's what it shows. ATD conversion status bit determines current status. When you have 1, means it's progressing, it's converting. But you need to set 1 yourself. You need to through programming. And this one 0, when it finishes, automatically throws out 0 on that line. Then you know it has finished. So these are the 2 registers that you need to know. The one I showed you earlier registers, ADCON1 register. And the second one is ADCON0 register. Let's move on to the next slide. Now we have reached a state, we can actually write a program. We can now write a program and for an ATD conversion. It's such a simple, 2 registers only you have got to program. Okay, the question is now, how are we going to program this? So what are the steps involved? Okay. First step is configure the port. You're going to configure the port. What port are you going to use? So port A, port B, I've already shown you previously. It's a 14 ports there. They are not in all 14 analog inputs, but they are between port A, port B, and port E. There are various pins can be programmed as an analog pin. So write a logic 1 into one of the press register, whether it's a port A or port B or port E. One of those press register, you configure them as input. So when you put a logic 1, it becomes input. Write a logic 1 to the corresponding ANSL register. So every one of them has got an ANSL register. You know that you have done that. As soon as you put 1 there, this input is no longer digital, it becomes as an analog input. So the computer expects, the microcontroller expects an analog input. Now you go back to your ADCO1 register. You configure the voltage references first. Remember, we said which voltages you want, you configure. Then you go to ADC clock conversion. You select the clock that you want, what frequency you want to operate. Then you select the input channel out of the 14, which one you want to select, which you already decided here. Then you say what format you want the output to be, whether it's just right justified or left justified. Then you enable the A to D converter. So once you have done from the two registers I explained to you, that and that need to be used for all of them. This is an optional one. Once you have enabled and start the A to D conversion, it can create an interrupt. When it finishes the conversion, one of the flag bits will go to 0, or it can create an interrupt. You can have an interrupt service routine where you read the data then. So if you want to use it as interrupt, that's optional. You can poll it or you can do interrupt. If you want to do interrupt option, you need to clear ADIF bit, because that's the interrupt flag bit. The AD stands for analog to digital converter. ADIF bit is here. It's in the PIR1 register at the location OCH. You need to access that particular. And then you need to go enable the A to D converter for interrupt. So that will be in the PIE1 register, ADIE, that bit. After that, you have to go to, these two are interrupt enabled that we have learned before, which are on intcon register. We have learned that global interrupt enabled and peripheral interrupt enabled. We have learned that before, so you have to enable all of those, and then you have to write an interrupt service routine. As I said to you, once you have energized your A to D converter, before you tell them to start to convert, once you have enabled them, you need to give a 20 millisecond delay, 20 microsecond delay for the system to settle, then only it will start to convert. If you try to, if you don't give the delay, and it may not give you the full answer. You may get some bits outside, but bits into the registers, but they may not be the accurate one. So you need to give that time. You start conversion by setting go down bit to 1 of the register. If the bit is set, it will start, and A to D conversion now starts. Polling is you wait in your program, check this bit, has it gone to 0? You set it as 1 to start the conversion. You have to now check it to see whether it's 0. If it is 0, then that's what you say. If it is 0, that means conversion is finished. Or you can wait for a to D interrupt as well. You can do this or that, one option, depends on how you select. If you use polling method, polling, waiting for it, or you do interrupt. Then you read the results and then save them. Now make sure you have to clear the flag bits before you go back. So I think now that's all the theory behind A to D converter. Now I'm going to give you an example, and I'm going to give you an example program. A variable analog signal is applied to an AN2, that's PA2. AN2 is here. A variable analog signal is applied there. While the results of conversion is shown in port B. So after you have done conversion, you normally have these two register 8 and 2 bits. What we do is we take the least significant least significant register bit, which is the 8 bits, and send the output to a port with an LEDs all connected, so the output is shown on LED. Port B as a binary. A positive reference voltage is applied to AN3. So we need to have a reference voltage applied here. Here, this is a reference voltage. So with reference to that, only we are going to measure the voltage. Basically, the difference between these two. So how do we do that? So basically, we need to make sure this has a reference pin, this one, and that's where you apply your signal. And the difference between this is what we are measuring. Difference between the voltage level is converted, 10-bit binary number. Only 8 lower bits of the result conversions are shown, because there are 2 more bits there. This is, if you say this is PB0, that's PB7, then we got 2 more bits coming, altogether 10 bits, but we're only showing 8 bits. That's what been given. You're going to program it now. Okay, let's go to the next page. How do we program it? So I've drawn both diagram for you. This is your reference voltage selection. This is your actual diagram. So the first one is, I know I have to, they're connected to port B, or their digital output. So select the ADRESH B register, clear all of them. That means all ports are output now, because we have connected LEDs. Then you move this pattern into W register by having, and then send them to shape. When you do that, this is PA0, PA1, PA2, PA3. This is PA2. This is PA3. We want both of them inputs. So I made that by setting all of the others 0, these two 1. So I made them as an input. Now I got to make it as analog input. So I go to bank cell and cell and put this pattern in there and move that to AND cell register. Once you have moved that one, you have set these to a 1. That means to configure a pin as an analog and appropriate bits are sent, and they're set to 1. So now it's been set as analog. And then you clear F and AND cell high. That means port B is now digital. So port B is a digital here. So you have done this enough, so you don't need to go through them. Only thing we have done is here is we made 1, so that it's become as an analog. So 2 pins are analog, then ports are all digital. So that's what we set up. Now let's start to look at our. So remember, first we need to go to ADCON register for A to D converter. And you go there and set this bit to 1 if you want right justified. That's what we're after, right justification. This is what we want. So I can only set that 8 bits. So so what I need to do is I need to set this bit, this is equal to 1. So I said bit set in that register, that bit. So I've set that to 1. That's just justified. Now I go to set these two ones. Remember, one of the voltage, that PA3 is reference voltage. So I have got to make it that as reference. So PA3 is here. I want this to be connected through this to that. That's what I want. That means I have to make VCF GO to 1. So I go VCO GO has to be 1. BSF, done. Then I need to get the next value, which is this one. This one is VCF G1. So VCF G1, this one, AN2, I don't want this to be connected at all. I want this one external voltage to go in there. So I want to connect this one to here. So I put VCF G1, this will be connected to ground. So I've made VCF G1 1. So voltage VSS ground is used as reference and RA3 pin is used as positive. So I've done both of them. And now I can use this as my input voltage. That is this voltage, RA2. And I've made this as a reference. So any variation with respect to that will be picked up. So that's the difference voltage I'm measuring. I'm measuring the difference between these. How I can do that? Making this as a reference, which is what I did, pin as a reference, and then I'm using the other one as an input. Now I go to this register. What do I need to do at the register? First, I have to access the register. Then I have got to set the oscillator. I want the oscillator to be 0, 0. So I need that bit 0, that bit 0. Because then I have a maximum clock frequency I'm running, F oscillation over 2. So I go there, my bits are, these two are 0. I made those two 0. Then I have to select a channel. The channel is RA2. That's my RA2 is my channel. So RA2, in order to select that in my reference, if you go back and relook at the previous page, and I can show you if you want to go back to see the previous page. It's some pages ago. Here RA2 is that. RA2 means I need to have 0011 in those registers. That's the value I need to have. So I'll come back again. Yeah, now. So I need to have in RA2, so I go 0010. Here you go. That selects me RA2. So I have selected these 4 values now. Then this one I can't do anything at this stage because I'm not ready yet. But then ADON enable bit. I'm going to enable my ADD converter. I have got to get ready. It's not started yet to convert, but I'm enabled them. So the whole circuit is ready now. So I need to set this to 1. So that's my 1. This bit is the conversion bit or conversion finished bit. We are not touching that in a minute. So I've done that one. So I've set my reference voltages, I've set my clock, I've set my input, and everything is enabled. But it's not ready to convert. So remember, once you have enabled them, you need to give them, for the circuit to settle, we need to give them about 20 microsecond delay. So I continue, I go to the next page. The program is not finished yet. So I've done the initialization, I go to the next page, I call a delay routine, acceleration delay of 20 microsecond. Right. I've done that. Now I am ready to start my ADD conversion. So I go to my ADCON register and I set this bit, go done bit, to 1. Once I set that 1, the ADD conversion process start. So that's what I've said. Bit, here, BSF 1, start conversion. Once I start to do the conversion, now I will check. This will be going to 0 when the conversion is finished. This is what I said. This will go to 0 when the conversion is finished. So I need to check this bit to see when it becomes 0. So I go in a loop. So I said, okay, I just put a no instruction. You can do without that as well. I said BTFSC. So I'm saying test if the bit is done. Is this bit 0? That's what I'm saying. Yes, if it is 0, conversion is finished. You jump. No, it's not 0. So conversion not finished. So you poll. You keep looping. You keep going. And when it's finished, you come out. That means your data, that conversion 10-bit, converted 10 bits available. So you now go bank cell address SL, that's the lower one. Move the value into the W, lower byte of conversion result is copied in the W register. I've done that. Then I bank select port B, and the W register is sent to port B. So that means whatever the 8-bit, I had 10-bit, I only can use the 8-bit. I'm sending to port B, mean these LEDs will show the number, the digital number corresponding to the analog voltage. Once I have done, I have to start a new conversion. This bit was 0. Now I got to set it again to 1 to start a new conversion. So I said BSF ADN, and then I go back to loop here and wait there, and it will do the second one. When that's finished, I send it to the port, and you can just keep doing that. That's A to D conversion, and measuring 2 voltages, difference between 2 voltages in this case. And the program is very simple. You only have to use 2 registers. That's all you have to do. Rest all the program that you have already done before. So I have another example for you to demonstrate as well. I haven't done this ADD conversion using interrupt at the moment, which I'll give you a question, you can try them out later on. But at the moment, just to get the principle. So let's look at the next example. What does this example says? This example is another example. Example 2, it says an analog voltage source is connected to a node. So just simply one voltage, varying voltage of port A of a microcontroller, which is set up to sample the analog signal and stores the 10-bit digital output in the location that and that. They want you to store the value, just one value. You can keep going and take the next value and so on, or overwrite it. But in this case, just one value. If you know how to write one value, you can do multiple afterwards. And also they're saying you need to configure the ADC for polling. That means you're checking, the same as the previous example. And VDD and BSS as references. What does that mean? Their references mean you need to go, that need to be selected to 0, so that is connected. That need to be selected to 0, so that is connected. That's what the reference means. And if you do that, then your A node, that line, is your analog line. And then you select, so, and they want you to select FRC clock. That means that bit is 1, 1, if you look back, and then this as the analog input, write an assembly language program. So first thing is that we select 2 locations. I mean, these 2 locations you select randomly. You can have any locations, but we know previous example, 20 and 21 are always empty, and we take those 2 locations. First one is for high, other one is low. Now we go through the same procedure as we did before. We say bank cell, ADC01 register, this register, and we want to make sure write justified. Write justified means this bit has to be 1, so I go move LW that. Right. And if it's only 1 bit, then you can use bit set. But instead of that, I want other thing as well. I want these 2 to be set as well. But we know to set that they should be 0, 0. So these are 0, 0. So I need to have a 1, 0, 0, 0, 0, 0, 0, 0. So that's what I have. So I've set this also in one go. So move that to, and I've set that one, I've set that one. Then I need to go to port A, because port A is my input, PA node. So I say bank cell to say, and I set the first bit RA node. I set the bit, that means it becomes as an input. Now I have to tell it's an analog. So I set ANSEL, select ANSEL, set that bit, the first, that corresponding bit, and that becomes as an analog. So I've done as an analog input. RA node is an analog input now. Once I've done that, that main part is done. Now I go and say, okay, let me go back to my this register. This register, now I got to select the clock frequency. Clock is FRC clock. That means the 500 megahertz one. FRC means these 2 should be 1. That should be 1. That should be 1 dB of FRC if you go back and look at it. And so these 2 should be 1. And it's the first port we are using as analog. That was the way it's going to go. So 0, 0, 0, 0. We don't touch that for the moment. Right? This one is enabling the A to D converter. So that's V1. So the value that we need to put is 1, 1, 0, 0, 0, 0, 0, 1. So you go there, move 1, 1, 0, 0, 0, 1, and then you move that into the into this register. So it's all enabled. Now what you need to do, call a delay routine for the system to settle before you can start the conversion. Call a delay routine, 20 microseconds. Once you have done that, 20 microseconds, now you go back and set this to 1. Go line, this goes to 1 now. You have to set that bit to 1. It starts the conversion. So I said that BSF is 1. Start conversion. Once you start conversion, you need to sit there and look when this goes to 0. So you need to do the polling. So you go and you say, I put a knob here. You don't need it, but you can put a knob. And I'm checking that particular bit, that not the 0th bit, first bit. If it's not done, if it's not 0, it will go back and loop. If it is 0, it commands from there and go to bank cell. Now I go to select the address H and move the address H value into the W register first, and then I move the W register to the digital high location, which is the H20. So that's where my 2 bits are there. Then I select the bank cell address L and move move the ADRESL 8 bits into W register and then move them back to digital low. That's all is stored there. And then if you want to continue running it, writing and rewriting again and again, if you want to do that, or if you want to write in a different location, you need to do indexing, and the same location you just clear, you need to go back and start the conversion again at the bottom and go back loop again. So you can repeat that if you want to do again and again. Normally you don't do again and again, you do again and again, but you write in a different location, the consecutive location. So if you write in a H20, 21, and then next two locations you can write, or you can write the two banks of memory, one writes the low, one writes the high, and you can switch between, or you have hundreds of ways of doing it. You store the data, later on you take the data out for further processing. So initially you do this ATD conversion, store the data first, whatever amount of data you want, and then you do the processing afterwards. Because you want to look at the data and see whether what's the maximum value, what's the minimum value, what's the DC component in the data, what variations are there, you want to measure that. So they are the two examples, simple example for ATD converter. Now I've got a laboratory activity. You don't need to try this out. If you have time after you submit your project, you can try it out. But very easy, you can write the program without even trying it out. Basically, I'm saying that here is the analog voltage source, voltage between 0 and 5. That means you need to select them accordingly. It's connected to RA node. And I have a switch connected to RA1. Every time I press this switch, so it's high, it goes to low. As soon as that, A to D converter should convert this into analog voltage, and that 8 bits should be displayed on the display. Now you press the button and release it, and then go again, press again, high to low. Every time you go high to low, it should do a conversion. So you got to test that. You need to clear these ones who are desired operation. You know what they mean. And you need to create a 20 microsecond acquisition delay. So it's a simple example. Almost all the code, all the initialization all required are in the previous two examples. You just pull them and put this program together and see whether you are able to do it. And it won't take more than 20 minutes to write and test as well in the lab. It's just to give you an idea of A to D conversion. Then you move this voltage up and down, change it around, look at these bits as well, and have a feel for it. Okay. That's all that chapter is, and again I have used these references. These references most of the time, and also the data sheet in order to write these lecture notes. Thank you.